I want to talk about a tool that's very useful for handling complicated problems of functions that are not polynomials. So just to get us started, I'm going to choose the function f of x equals e to the x. And what I have in mind here is things like integrals involving different types of functions, maybe compositions of functions involving e to the x. We could do more complicated equations that involve different derivatives and integrals. So quite complicated equations. I want a way to rewrite e to the x in a way that's really simple and at the same time gives me a very strong handle on getting really nice approximations for all of the solutions to those different types of problems. So the way I'm going to do this is I'm going to start approximating e to the x using really simple polynomials. So first I'll just use a constant polynomial. And I'm going to center my approximation at x equals 0. So if I'm centering at x equals 0 and I want to approximate with the constant function, then it's going to be this constant 1. So my constant function would just be y equals 1. I'm going to write e to the x down here, starting with these approximations. So first, it's approximately equal to this. Then, if I want to bump up my approximation, instead of being constant, I'll let it be a general linear function. So I'll look for the tangent line. My tangent line will have the exact same constant at x equals 0. So I still need 1 as my constant term at x equals 0. But I want to take into account the slope of the tangent line, which is the derivative of e to the x, evaluated at x equals 0. I know the derivative is e to the x, and if I evaluate that at 0, then I get 1. So my slope needs to be 1, so I would do plus 1 times x. And now if I want to get a quadratic function to approximate this thing, I want my quadratic function to still have the same constant at x equals 0. It will still have the same slope of the tangent line, but I want to get my hands on the concavity somehow. So I'm going to have a parabola that looks maybe something like this. That will be a better approximation than just the red line. So I need plus something times x squared. And the something, I'll just call it C2 for now. It's a constant of the second degree piece of this. What I know is that I want this approximation to have the same concavity as the function e to the x. So I'll take that concavity, I'll take the second derivative, which is still just e to the x. I'll evaluate it at 0. I still get 1. So I want my concavity to be equal to 1. The way I can do that here is I can take the second derivative of my approximation. So notice, even when I put this extra piece on here, my first derivative, let's call this p2 of x. The first derivative of that thing is 1 plus 2c2x. And so the first thing I want to point out is that if I get the slope of the tangent line for this quadratic, the slope of the tangent line at x equals 0 knocks out everything bigger than this first term that came from the coefficient of x. So it will still have the same slope of the tangent line as we did for when we just had the linear piece. And you're going to see, well, that will continue to happen because I'm going to build this up piece by piece, term by term, x cubed, x to the fourth, and so on. And I'm evaluating at x equals 0. It's going to no matter how big I build it up, how many terms I put on there, it will still have the same slope of the tangent line. It will still have the same concavity. It will still have the same generalization of that for the third degree and the fourth degree and so on. So if I just build term by term like this, I'm not going to mess up anything that I put on it before. So the derivative, the slope of the tangent line here at 0 is 1, just like we want it to be. And the second derivative is 2c2. And notice if I had x cubed and x to the fourth and so on up here, then when I take that second derivative, those terms will still have x's in them. And when I evaluate that at 0, they will all go away. So the concavity at x equals 0 will still be 2 times c2. And I want the concavity of p2 of x to be the same as the concavity of e to the x, which is 1. So I want to set that equal to 1, and then solve for c2. So I get c2 equals 1/2. I can come back and update that. And now I'm ready to go grab the third term. And I can continue this process and keep finding these. And what's really nice about this is that if I keep doing this, I get better and better approximations for the function as I add more and more terms. And then if I take the limit as the number of terms goes to infinity, I get the exact function. Now, even though I get an expression for the exact function, I'm not guaranteed yet for that expression to converge to the correct finite numbers for all values of x. But for sure it works at x equals 0. And then the way it works is, as you move out from x equals 0 in both directions, there's a nice way that you'll learn eventually to figure out what values of x this expression works for to give you exactly e to the x. I want to do this in a more general format, and I want to show you that there's a nice pattern for finding all of these c's, all of these constants. So I'm going to do that now. I want to move to a more general function, so this should work for logarithms, roots, trig functions. One thing that I will need is for the derivative to exist at each point. So wherever I'm centering, I want it to have infinitely many derivatives. So I'm going to move on to a general function, f of x. And I don't know the constant yet. I don't even know what the function is, so I'm going to call it c0. And I'll have c1x, c2x squared, and so on. And what I want to do is show you the pattern for finding these constants. I'm claiming that it can be done pretty easily for all the constants. There's a nice pattern. So the first insight is we can always get this constant by just plugging in x equals 0. So I'm centering this. This is called a Taylor series. And specifically, I'm centering the Taylor series at x equals 0, like I did in this example. You can center it at any x value you want, and I can show you how to do that. It's really simple. There's another technical name for a Taylor series centered at 0. It's a Maclaurin series. Not necessary right now. If I plug in x equals 0 on both sides, I just get c0 on the right. So that's easy. Now I want to find c1 for this general function f. You might guess that maybe I could plug in different numbers instead of 0, to try to get my hands on C1. You can pause the video and play around with that a little bit. I don't think you'll get very far if you do it that way. Another way that you can try manipulating both sides of the equation so that you could get your hands on C1 is to take the derivative of both sides of the equation. The reason that's helpful is that the first constant term goes away. The C1x term turns into just C1, which is what we want to solve for. And then all the other terms will still have an x in them. So when we plug in x equals 0, they will all go away. So take the derivative of both sides here. You get C1 plus 2C2x. And I'm going to write down more terms. 3C3x squared, 4C4x cubed, and so on. It follows a pattern that we could write down fairly easily. Maybe it would be good to go ahead and write that. I'll leave it alone. Once I have this, then to solve for C1, I just plug in x equals 0. All of these terms go away. I have C1. So, I told you there's a nice simple way for finding all these constants. At this point, you may say, oh, to find C2, I'm just going to do f double prime of 0 equals C2, and to find C3, third derivative evaluated as 0. Let's check that and see if that actually works. If it does, that would be awesome. Let's take the second derivative. This goes away. I get a 2C2 plus, I'm going to write this in a weird way. 3 times 2, it was 6. It's 3 times 2, C3x, plus 4 times 3, C4x squared, and so on. And now to get C2, I plug in x equals 0. I get 2C2 plus, and then all the other terms do go away, just like I wanted. But notice, now when I solve for C2, I get 1/2 of what I thought I would have. So the pattern is not quite as simple as I thought it might be, just by looking at the first two. So I need to keep going and see what I end up with. Let's take the third derivative, and then we'll try to draw the pattern from that. So the third derivative, I'm looking at this line. This goes away. I get 3 times 2 times C3, 4 times 3 times 2 C4x, and then I'm going to try to guess at the next term. The next term would have come from originally x to the 5th. So when I took the first derivative, I would have a 5, and then when I took the second derivative, I would have picked up a 4, and the third derivative would have given me a 3, and then I would still have 2 powers of x left instead of 1 like I had for the previous term. Oh, and there's a C5. And then it keeps going. So I'm going to remember this off to the side. F of 0 was my original constant. Then f prime of 0 was C1. And then C2 was 1/2. The second derivative evaluated as 0. So now I want to find C3. You can see how to do that. I'm going to plug in x equals 0 here. All of those terms go to 0. So C3 is 1 over 3 times 2 times the third derivative evaluated as 0. There's a reason why I'm writing it this weird way. Now I want to guess at what C4 is. To get C4, I would take one more derivative here. So this first term would go away, then I would have just this, and then every other term has an x in it. I plug in x equals 0, I'm left with just this. So this constant is equal to the fourth derivative, evaluated at 0. Then I solve for the C4. I get 1 over 4 times 3 times 2 times the fourth derivative, evaluated at 0. When you get above the third derivative, people usually write the derivative as just the number inside parentheses. Look at this pattern that's happening. For my next one, for C5, I would have 1 over 5 times 4 times 3 times 2. So there's a way to write this pattern. You may already know what it is. It's called factorial. So here, 3 factorial is 3 times 2 times 1. 4 factorial, 4 times 3 times 2 times 1, and so on. 5 factorial would be the same, but with an extra 5 there. So this is 1 over 4 factorial, 1 over 3 factorial. So for C5, it will follow the same pattern. I'll have 1 over 5 factorial times the fifth derivative, evaluated as 0. And we could write the general constant now. The general constant, Cn, for the nth term, will be the nth derivative, evaluated as 0, over n factorial. So now remember in that original expression for this very general function f, that could be exponential, logarithm, trig functions, other types, we can write out exactly what those constants are for all of those, for any of those. This is extremely nice. It's a very powerful tool. I'm going to make at least a couple of videos looking at specific examples of this. I'll look back at e to the x now, and probably 1 or 2 others. But I want to go ahead and write out the general form for the function now. The compact form of the Taylor series using summation notation. So up here, I'll remind you of what we had. We had C0 plus C1x plus C2x squared, and so on. I want to write that starting at 0, so I'm going to start at 0. I'll go from n equals 0 to infinity and then I'll basically have Cn times x to the n. But Cn is this thing. So it's the nth derivative at 0 over n factorial. That's the Taylor series centered at 0. If I want to shift this to some other value and not be centered at x equals 0, that's no problem. What I need to do is find the constant, the slope of the tangent line, the concavity, and so on at that specific point. So if it's x equals a, then I evaluate all of these derivatives at a instead of 0. And then I shift the graph just like you would normally shift the graph of a function by replacing x with x minus a. So if I'm shifting to the right by 5, if I'm centering at 5, I would take all the derivatives at 5, and I would do times x minus 5 to the n. That's the Taylor series. You can do a tremendous amount of work with this thing. I hope you have fun with it.